So I will start with, again, some examples, in fact, following my last lectures. I did several examples of metric spaces and Finsler manifolds, and I will continue with this. Let me mention that our friend, what's your name? Yes? Yes, Hayeb solved one of the questions which I said about the triangle inequality. In fact, you must use trigonometry, and this is what she did. And I will talk now about trigonometry also, which will be useful in my next example. And this is something about non-Euclidean trigonometry. I will make a few. I will recall a few things about hyperbolic and spherical trigonometry. First on the sphere. So suppose our sphere is the usual sphere in Euclidean 3 space, and I suppose that it's radius 1. And then, as several people here, I don't remember who talked about this, but we have these great circles who are the geodesics sphere. So you see, each time a plane cuts the sphere, it cuts it in a circle. This is a theorem of. This is a theorem which you can prove easily. So I cut my sphere with this plane. I get a circle. In this plane, and the circle is called a great circle if it has maximum radius, and this is if and only if this plane passes through the origin of the sphere. So the great circles are the intersection of the sphere with the planes passing through the origin, and as you already know, in fact, probably not by spherical geometry, but because you know this, that the great circles are the shortest lines between 2 points on the sphere. Shortest lines for what? In fact, shortest lines, geodesics, and shortest lines for the spherical metric. And what is the spherical metric? The distance between this point and this point. This is the angle. This is the angle alpha made by the two rays which start at the origin of the sphere and which pass through these points. So the maximum distance between 2 points on the sphere are where my 2 points are diametrically opposite on a great circle. So the maximum distance of 2 points of the sphere is pi, right? The angle is pi. The maximum distance is pi. And I said I want to talk about trigonometry. Trigonometry on the sphere. So the trigonometry, as you know, this is you have a triangle, and you want to have formulas or theorems which relate the angles of this triangle with the lengths of the sides of this triangle. Okay, so where are my triangles here on the sphere? So I take my sphere. I take one of these straight lines. Now I call it straight lines in the sphere. It's geodesics or great circles. Then I take a second one like this. And then I take a third one like this. Like in the plane, you take 1, 2, 3 lines. You find a triangle. On the sphere, you take 1, 2, 3 lines, and then you find a triangle here. In fact, on the sphere, I find how many triangles if I take the intersection of 3 lines. Can you count how many triangles I find? Yes, 8. In fact, I only hear the girls. There are more. I heard 2 or 3 girls saying 8. I didn't hear any boy saying 8. So I have. So there are 8 triangles. 8 triangles. You can count. This is one. This is a second one here. This one here. The vertex is here, and then this is the second, and this is the third vertex. And so these 8 triangles. We want to find trigonometry of this triangle, but at the same time, I can find the trigonometry of the other triangles. In fact, it's easy to know that if you find trigonometric formulas for this one, then you find also the trigonometric formulas for the other one, because you see the angle here is equal to the angle here, and the lengths. You see, the angles are determined. The 3 angles of this one determine the 3 angles of all the other triangles. Okay? And now it's a theorem of spherical geometry, which does not hold in Euclidean geometry, is that the 3 angles of a triangle, they completely determine the triangle. In Euclidean geometry, it's the 3 sides completely determine the triangle, completely determine the triangle up to isometry. In spherical geometry, it's determined by the 3 angles. The lengths of the side are determined by the 3 angles. So the 3 angles of all these triangles are determined by the 3 angles of this one, so everything is determined. So when I draw 3 lines, I have 1 triangle, and the others are more or less the same triangle, but with different, different configurations. This is not. This is just a side remark. So I have a triangle, and I want to find a formula for the relating the angles with the sides. You can derive formulas. In fact, this is a classical subject. This is a classical subject. The spherical trigonometry. The Indians worked on this. The Indians worked on this long ago. The Greeks also worked on this, I think, before the Indians. Euler, whom you all know, worked a lot on spherical trigonometry. This is one of his favorite subjects. So I don't want to say much about this, but I want to give you some examples of trigonometric formulas which I will use. So this is one of them is the. Okay, this is the sine rule, and let me put here while this is Euclidean sine rule, and this is spherical sine rule. So the Euclidean sine rule, I have a triangle here, A, B, C, and then with the side lengths A, B, C. The Euclidean sine rule tells you that A over sine of A equals B over sine of B equals C over sine of C. This is the Euclidean sine rule. The spherical sine rule is so here I have, instead of the Euclidean triangle, I have my spherical triangle ABC with the side lengths ABC. So here it's sine A divided by sine A, sine B divided by sine B, sine C divided by sine C. It's not too difficult to derive this formula. You can try to derive it as an exercise, and there are several ways to derive it. One way is to use projections and to use the Euclidean triangle which joins these three vertices, the Euclidean triangles which you see in three-dimensional space. It's not the best proof, because there are proofs which use only the geometry of the sphere and which do not use at all the ambient space. Okay. So this is the sign rule. I want to. So I have another formula which I want to which I will use, in fact. So, and again, this is now for a. This other formula is for a right triangle. For a right triangle, I have okay, A, B, C, and the right angle at C. So this would be here on the sphere. This would be here. I have a right angle, and then this is C, this is A, this is B. So I didn't tell you how you define the angles of this triangle on the sphere. I told you that the length is defined using the Euclidean angle at the origin. This is the length. Now the angle of a triangle here, you know that these two sides are intersections of planes with the sphere, and the angle they make is the angle that the two planes make. This is Euclidean geometry again, three-dimensional Euclidean geometry. When you have two planes in space that intersect, there's a well-defined angle. It's called the dihedral angle. So the dihedral angle of this, the dihedral angles of this space, the dihedral angle made by these two planes is the angle at that vertex of the triangle. So here I'm supposing that my triangle is a right triangle. It has a right angle, and then in Euclidean geometry I have sine B is equal to B over C, right? This is sine B is equal to no, it's here sine of this angle. No, sorry, sine. Okay, so this is B, this is C. Sine B is equal to B over C. In spherical geometry, it's sine B is equal to, well, somebody can guess here, sine B over sine C. It's not always the case that you have to replace the length by the sine of the length. It would have been too easy, in fact. But let me give you the third formula. So this is cosine B. Cosine B. This is, in the Euclidean case, this is A over C, and here cosine B. In fact, this is tangent A over tangent C. So why is this? Why is this? This is a good question. Why do you have to? I mean, why do you? There are many similarities between these formulas. Many similarities, as you can see. And to understand why we have all these similarities, you have to work a little bit on spherical geometry. Then you understand. Now I want to make a few more comments. So I said I will talk about hyperbolic geometry. So this is Euclidean. This is spherical, and now here I put hyperbolic. So this is constant curvature -1, this is constant curvature 0, this is constant curvature +1. So in the hyperbolic plane, let's say you have a model. This is a geodesic. This is a geodesic. We also saw this several times in this class. So we must take 3 geodesics that intersect. This is a second geodesic. And then say, okay, this is also a third geodesic. And here I find this small triangle. This small triangle, which I call ABC as before, with the 3 side lengths, also small a, small b, small c. And again, the trigonometry here is something where is some formula which gives me relations between sides and angles, and there are many. In fact, these are only 2, but you have, as I mentioned, Euler. In fact, Euler wrote several papers on spherical geometry or spherical trigonometry, where he derived all sorts of formula. He has pages and pages of formulas of relating sides to angles. In fact, you have you have many possibilities, more possibilities than in the Euclidean case, since, as I told you, you have formulas giving the lengths of the sides in terms of the angles, which you don't have in Euclidean geometry. So hyperbolic, now, to write these formulas, it's very easy for me because I know the result. And here you see the sine formula. You have to replace every time you find a sine here, you have to replace it by hyperbolic sine. Every time you have tangent, you have to replace it by hyperbolic tangent, and so on. So it's very pleasant. To find the reason is something else. To understand why this is the case, you have to work a little bit and to think about it. But anyway, here the sine formula is sinh A divided. So you don't put sinh here, okay? The angles, in fact, you will notice that the angles in this formula, you don't change them at all. You change only the lengths. So the angle is state sine of the angle, and here it is sinh B divided by sine B, sinh C divided by sine C, and here I can write it automatically, sine B equal sinh B divided by sinh C, and the last one, cosine B equal to sinh A divided by sinh C. So these are the trigonometric formulas of the, some of the trigonometric formulas of non-Euclidean geometry. Let me mention also some other formulas. So that you understand how it works. So I have here. Is this okay? Yes, please. Yes, you are right. You are right. Here it's, thank you. Thank you. So it is hyperbolic tangent. Thank you. So everybody, those who take notes must correct this. I want to give a couple of theorems, in fact, to show you also how this works. I mean, how the automaticity of this works. So the first theorem I call it a proposition. In fact, somebody also talked about theorems and propositions. For me, there's no difference between a theorem and a proposition. If you look in Euclid's Elements, everything is a proposition. There's no theorem, in fact. A theorem, a proposition means a theorem. this is the, so in the well, let's say, okay, so the perimeter of a circle of radius r, perimeter of a circle of radius r. So let's see, in the Euclidean geometry, this is 2 pi r. Okay. In the spherical case is 2 pi sine of r. In the hyperbolic, it is 2 pi sinh of r. So now you understand this. Okay. Does somebody know the formula for the area? The area of a circle of radius r, the area of a disk of radius r? Yes? No, in the Euclidean case I know it. But I want it in hyperbolic and spherical. I mean, you can not guess it from here, but does somebody know what is the response? No. Okay. So this is something you can check. You can check. I mean, you can try to prove, or if you are interested, you have to spend, you have to invest some time to prove this, but it will give you. I mean, it's a very good exercise, or you can check on in a book. So there are similar formulas for area. This I don't. Well, I will use it later, but now I don't need it anymore. I want to give you, in fact, two other propositions. Two other propositions which are useful. One is the so-called Ptolemy theorem. Let's start by the Euclidean. So Ptolemy's theorem is, you have a quadrilateral. Let's cheat a little bit. So a quadrilateral ABCD. So everything can be proved using the trigonometric formulas. The trigonometric formulas, in fact, they prove everything you want in geometry. All the geometry is contained in the trigonometric formulas, because when you know the lengths of the relations between lengths and sides of the triangles, small triangles, then you know the infinitesimal lengths, and you know the big lengths, and you know everything. So the trigonometric formulas are the basic of everything. With these trigonometric formulas, you can prove this Ptolemy relation, which I will say now, the Ptolemy's theorem, which tells you this is a necessary and sufficient condition for the quadrilateral ABCD to be inscribed in a circle. So let's start with the Euclidean case. The Euclidean case. So you look at the diagonals. So you take an arbitrary quadrilateral. You have the two diagonals. So here also you have. I want to call them. I don't need the vertices. In fact, I want to call them A, B, C, D, the lengths of the sides, and E and F, the two diagonals. And somebody knows this relation? What is the relation for the Euclidean case? I want a relation between, yes, you're right. But this is not what I want. I just want a formula which relates A, B, C, D, and E, F. What is the formula? Maybe Uludag knows. What is the formula for the Ptolemy theorem? Well, the formula is AC plus DB equals EF. This is the Ptolemy theorem. And you can prove it also using trigonometry. This is the formula for Ptolemy. Now, in the spherical case, it turns out, you saw from my table here that you never know. So, I mean, if you don't do the proof, you never know whether you put sine or sinh or something. But you can guess. In fact, in mathematics, you know, we have analogies. That the analogy would tell you that I will put here sine. In fact, it's correct. In the spherical, it is sine A, sine C, plus sine D, sine B equals sine E, sine F. So in this, you see, in the spherical case, I didn't tell you what is a circle, in fact. I told you what is a line on my sphere. This is a great circle. A line is a great circle, but a circle, in fact, is, okay, you have a point, and then it's a set of, it's the set of points which are equidistant. It's a set of points which are equidistant from this point, so this is what is called a small circle. And it's also the intersection of the sphere with a plane. So the intersection of the sphere with a plane is either a small circle, which we call a circle, or a big circle, which we call a geodesic. Okay? So you have circles on the sphere, and then you have quadrilaterals. You know, the quadrilaterals are just these intersections of the, quadrilaterals are figures obtained by joining 4 points by geodesics, which are the intersections of the sphere with great circles. Okay, so this is so you know what is a quadrilateral on the sphere. You know what is a quadrilateral inscribed in a circle, and the relation is this one. So it's inscribed in a circle if and only if, and then now you can spherical Euclidean. Here is hyperbolic, and here you have sinh A, sinh C plus sinh D, sinh B is equal to sinh E, sinh F. This needs a proof, of course, but it's a theorem of hyperbolic geometry and of spherical geometry that a quadrilateral is inscribed in a circle if and only if we have this. Now, I told you that Euler worked a lot on spherical geometry, so he has 2 kinds of papers. One paper is on trigonometry, deriving the trigonometric formulas for the sphere. He has maybe 2 or 3 papers on trigonometry, and the other papers, in fact, he has maybe 12 or 15 papers on spherical geometry. In the other papers, he systematically takes a well-known theorem in Euclidean geometry, and he proves the analog in spherical geometry. Okay. He did not do this because this was already known, in fact. This was already known by people who worked on spherical geometry before, but he did several other theorems, in fact, on spherical geometry. Several other theorems. In fact, I could give a course on this. Anyway, it's easy to imagine theorems. In Euclidean geometry, you take Euclid. You take a random proposition and you ask yourself, is it true in spherical geometry? For instance, the proposition which says that the three medians of a triangle meet in a common point. Can you prove this in spherical geometry? This is not very difficult, but the same question for altitude is more difficult. And there are other theorems in Euclidean geometry which you can try, in fact. And Euler tried several theorems on Euclidean geometry. So he had a book. This is the book by Pappus of Alexandria. This is a book, a thick book, which has a lot of theorems of Euclidean geometry, many theorems of Euclidean geometry, and one source for problems for Euler was to take theorems of Pappus and to see whether they are true in spherical geometry. And each time he found a proof, then he published it as a paper. And there are many theorems in Pappus' book, which is called the Collection, in fact. The Collection. I think, which are worth examining in spherical geometry or in hyperbolic geometry, because we know hyperbolic geometry. We know a little bit more than Euler. In fact, we can ask the same question in hyperbolic geometry. It's not automatic. Some theorems do not hold. Some theorems in Euclidean geometry do not hold at all in spherical geometry or in hyperbolic geometry. You have to work and to see whether they work. Okay, and the last theorem which I want to mention is a theorem about let's put it here, a theorem about invariance of cross ratio Let me tell you what is the invariance of cross ratio in Euclidean geometry first. The Euclidean case. Let's do the Euclidean case. So the configuration is like this. You have 1, 2, 3, 4 lines which intersect at a point. Then you take another line which intersects these 4 lines, and you call these points A, B, C, D. And you form the cross ratio of these 4 points. Now, I talked in the first lecture about the Hilbert metric. It involved the cross ratio. And the Hilbert metric was the symmetrization of the Funk, remember? So I know how to write this cross ratio. This is because I want to write the Funk distance here. So it is BD divided by BD divided by CD plus, you see, remember we had logarithms and so on, so here we have to multiply, plus, multiply now by CA divided by BA. This is the cross ratio of ABCD. And the theorem here, the invariance of the cross ratio, tells you that if I take another line which cuts this one, which catch these 4 in A prime, B prime, C prime, D prime, then this is equal to the cross ratio of A prime, B prime, C prime, D prime. Which is B prime, D prime, C prime, D prime times C prime, A prime, B prime, A prime. This is the invariance of the cross ratio. And this theorem in Euclidean, let me put it here in blue, in the spherical case. The spherical case is, the figure is the following one. The figure is the following one. You have the sphere, and then you have 4 lines on the sphere, which means four great circles intersecting in one point, and you take another great circle intersecting them, and you find points A, B, C, D, and then you take another great circle intersecting these 4 lines in 4 other points, A prime, B prime, C prime, D prime. And there's an invariant, in fact, here. There's an invariant in the spherical case. The invariant is, this is a spherical cross ratio, and here you have to put sine, 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 sine. So this is the invariance of the cross ratio in spherical geometry. And I don't want to say a lot. Now you understand that in hyperbolic geometry you have the same invariance of the cross ratio. So this is 1 line, 2 lines, 3 lines, and 4 lines. And then again you have a how will I do this? Okay, how will I find that? Okay. Okay. No, what do you mean by no? I don't know. So you have a line which cuts them, the 4 of them. Anyway, it doesn't matter. You have to do. Okay, let me do. Okay. Anyway, this is you can think of it as an exercise. So you have the line, and then here you have to put the sinh. In the hyperbolic case, instead of the sine, you have to put the sinh. Let me mention that. This invariance of the spherical cross ratio was also known since. It was known since Greek antiquity. This is a theorem of Menelaus of Alexandria. He has this theorem in a famous book called the Spherical Geometry. So okay. So now what we learn from all this is that there are theorems, in fact, in spherical geometry which are analogous to theorems in Euclidean geometry and which are worth proving, I think. And also the hyperbolic case is also worth examining. And I want to give you a few. Mainly two examples of such things. And you see, I gave you 5 or 6 examples of metrics, in fact, on which you can say a few things, at least the geodesics, the circles, things like that. And there are other things to investigate for these metrics. So I think all these metrics, you can study them in a hyperbolic or in a spherical setting. And I want to talk about some of them. So I start with the first one. This is this is the Funk metric. So the Funk metric, as you remember, it was associated to a convex set omega in Euclidean space or in the plane. In the plane, it's already interesting. We don't have to think about 3 dimensions. And the formula was f of xy for 2 distinct points x and y. The formula was the log of the Euclidean distance from x to b divided by the Euclidean distance from y to b. And I want to do this on the sphere. So I have to, no? Is this correct? So I have to first to define a convex set on the sphere. So I have my sphere. And then you see on the sphere you have to be a little bit careful, because I want to say, in fact, that whenever I take 2 points on the sphere, then the geodesic that joins them is contained in that convex set. Whenever I take 2 points in the convex set, you have to be careful about a few things. You see, if I take, for instance, if I take the upper hemisphere, well, let's take it an open set. Let's take it an open set. So the upper, you see, the point is that I just want, the thing I want to mention, and where you can get into trouble sometimes, if your set is too large, say greater than the hemisphere, then you take 2 points here. Okay, the shortest line that joins them is this one here. It's in my set. But if you take 2 points here, 2 points here on the diameter, then you have this one, and then you have this one, and so on. There's something to care about here on the sphere. It's not important, but you have to care about if you work on the sphere. So for convex sets, you better take them all strictly contained in the hemisphere. Okay, and then when you talk about the geodesics joining them, you talk about the shortest distance, not any one of the parts of great circles. So this is not an important thing. The important remark I want to make. A is, and I thought about this a couple of days ago when Izmestiev was talking about support hyperplanes. You see, here the convex set, any convex set in Euclidean space. So for any convex set, if you take a point, say on the boundary of this convex set, let's take a convex body like in his talks. There's a plane here. There's a plane, in fact, a hyperplane which passes through this boundary point, and where the whole convex body is contained in one of the two half spaces bounded by this hyperplane. Okay, we saw this. In fact, he gave you a proof. In fact, and the proof involved linear algebra. In fact, there was a function with so there were planes defined by linear equations and so on, and he was maximizing, minimizing. So on the sphere, there's exactly the same thing. There are on each point on the boundary of my convex set, you prove that there is a support hyperplane. A support hyperplane meaning here in this hyperplane in this two-dimensional case is just a line. It's a great circle, right? It's a great circle. It's a great circle. So the great circles that are support hyperplanes exist, but you cannot at all use the same proof because you don't have linear algebra here. You have to reason more geometrically. In the hyperbolic case, also you have a convex set as same kind of definition. Any 2 points you can join them by a geodesic, and this is convex. And you want to find a support hyperplane passing through this point, and it does not. Of course, you can cheat. You can take models in Euclidean plane and take Minkowski model or whatever here, and talk about linear algebra. But this is not the right thing to do. You have to. You see, I'm talking about the sphere, the hyperbolic plane, and the Euclidean plane or Euclidean space. But as you can imagine, you can do this in any in more general spaces, right? So, for instance, let me mention this. There's something called, well, the Funk-Weil-Peterson metric. This was used, in fact, it was defined and it was developed by my colleague and my friend Sumio Yamada. After I explained to him these things about Funk metric, you see, the Funk metric, you have an underlying space. So his underlying space is Teichmüller space, and then you have a convex set in that space, right? And you want to use the underlying metric like this. I'm using the underlying metric to define a new metric on this space. So you want to define convexity, and to use convexity in principle in any space you like, any metric space. You can define what is a convex set or convex body or whatever in some metric space, which has. Then after this, you need to put some hypothesis. You need to know, for instance, existence of geodesics, maybe uniqueness. You need extension of geodesics. You need to know how to extend geodesics and so on. And people thought about this. Mainly, Herbert Busemann thought about this, about intrinsic geometry, of manifolds. What do you need to define convexity in an arbitrary metric space, which with some arbitrary, but with some conditions. In fact, he had these G spaces, which have to do with existence of geodesics locally, and he has these better, more precise spaces, and the G spaces, which he called these Argesian spaces, where the only thing I'm saying here is that convexity is not proper to Euclidean geometry. You have to, you can use convexity and study convexity and define properties of convexity in any metric space. So this existence of support hyperplanes using the linear algebra will not work, in fact. So anyway, for the Funk metric on the sphere and in hyperbolic space, you have these existence. You have this existence of support hyperplanes, and in fact, there's a theorem. There's a theorem which I'm not sure that Izmestiev mentioned it. In fact, not only the convex set has all these support hyperplanes, but the convex set is the intersection of all these half spaces bounded by the support hyperplanes. So the convex set itself, you can define it using these support hyperplanes. Okay? So now I want to give I want to tell you how I'm using this, okay. Again, let's do first the Euclidean case. I erase the figure and I'm doing the same one, but almost the same one, not exactly. X, Y. And let me cheat a little bit. This is my support hyperplane, and this is here X and Y, and this is B, and this I'm taking the support hyperplane at B. And from X, I'm taking this perpendicular, which I call X prime, and from Y, I'm taking this perpendicular, which I'm Y prime, and then I can write the Funck distance, which is this log of this divided by this, as log, well, the distance from X to X prime divided by the distance from Y to Y prime. Okay? And in fact, so this is very easy. This is just planar Euclidean geometry, similarity of these two triangles. And in fact, I have this formula, which is a little bit more complicated to prove. And this is, in fact, the supremum, well, over all pi, where pi is support hyperplane, over all support hyperplanes. I don't want to add notation, but let's take the same thing. Here I'm taking the same thing, but x minus, well, x prime pi divided by y minus y prime pi, where now I'm taking here not only this hyperplane, support hyperplane, which passes through this point B, but an arbitrary hyperplane pi, and I'm taking the distance from X to this hyperplane, and the distance from Y to this hyperplane, and this I'm calling X prime pi. Here I'm calling Y prime pi. And I'm saying that this first thing here, where I take this point here, in fact, it is greater than all these ratios. You see, you can see here this ratio is almost equal to 1 here. Well, it's not clear on my picture, but this is now a formula which you have to prove. And the proof is the same, more or less, as our friend here did when she proved the triangle inequality. And in fact, it is indeed useful for the triangle inequality, because if I use this formula for the distance with the supremum of all, the supremum over all support hyperplanes independently of this point B, then the triangle inequality is automatic, right? Because I'm taking supremum over the same thing. I'm taking the supremum over the support hyperplanes to my convex set. So when you prove this formula, you have automatically the triangle inequality for the Funck metric. Okay? Now, my next remark is that you see, you are when you have such a formula and such a formula, then you remember, now we want to do the same thing in spherical and in hyperbolic space, and I'm using these ratios. I don't have at all these I mean, this divided by this is not equal to this divided by this in spherical or in hyperbolic geometry. I don't have similarities. These triangles are not similar. But from one of the formulas I showed to you, namely the formula for the sine of this angle, it tells you that, in fact, so here we have right triangles. The formula tells you that what? It tells you that so there's a similarity. You see, this formula was in spherical geometry. I had an angle B, and then I have the sine of B. So this was B here, and this was C here. The sine of B was sine of B divided by sine of C. Remember this formula? So it tells you also that, well, if I take here a perpendicular, so this was a perpendicular. If I take a perpendicular, then the sine of B is also equal to, let's call this B prime, and here this one C prime. So this is sine B prime. So B prime is this one, and C prime is this one here. So this is sine B prime divided by sine C prime. So these triangles are not similar in spherical geometry, but I have this relation like for similar triangles using, but inserting the sines. Okay, inserting the sine. And in hyperbolic space, I have the same thing in inserting the hyperbolic sine. So with all this, you can define this. I mean, when you have noticed this, together with Yamada, and I remember that paper we wrote with Yamada. So it was after a conversation with Norbert Acampo we had this idea. So of defining it this way. So we have. So you have the spherical Funke metric f of xy instead of, so it's the same thing. You take a convex set. You take a convex set in the sphere. You have A and B. No, you have x and y, and this point B. So this is the logarithm of now here I put x minus. Well, here first I have to put sine of. Let me put it now. The distance. This is the spherical distance between x and B divided by the sine of the spherical distance between y and B. And we have the same formula here, except that the same formula for support hyperplanes, except that here, instead of the Euclidean distance, you must put the spherical distance. Here you put spherical distance. You prove the triangle inequality, and so on. And then you try to prove everything you know about the sphere, the Funke metric. Not all the things work. Some of them work. You try to prove everything you know about the Funke metric for this spherical Funke metric, and of course you have also the hyperbolic Funke metric, which you can also study. And in fact, you can imagine other spaces. For instance, complex projective space. You see, you can if you know a little bit about complex projective, not complex projective, complex hyperbolic space. you can, so it's the situation there is more complicated. You have all sorts of different sorts of lines, of triangles, of so on, but it's conceivable that you can do this. You have trigonometric formulas, and in fact, some people already developed trigonometric formulas in complex projective, complex hyperbolic space. The theory is surely interesting, and then maybe so I want to stop here because it's finished, but you can ask, what about the Finsler geometry? What about the Finsler geometry of this? Last time I explained to you that the Funk metric is a Finsler metric. I can explain to you next time why this is a Finsler manifold, a new Finsler manifold. And then you can symmetrize and study the Hilbert. The Hilbert spherical and Euclidean spherical and hyperbolic metric, and then you can have the exterior, that is the time-like Funk and Hilbert metrics. You can study their properties and so on. So I never checked the other metrics. You see, there's this. I defined this metric, the semi. One of them is the semi-Apollonian. I never checked what is the situation in hyperbolic or spherical geometry, because it was sufficient. I mean, for us to study this one, but somebody can study the semi-Apollonian, and so all these are examples of Finsler manifolds, in fact. Some of the metrics I gave you were not Finsler, but all these are Finsler manifolds. So, okay.